All right, so the most important news is exam on Friday. And the topics are everything up through the first law for control volumes. And remember that all my quizzes, all my tests are cumulative. So be ready for stuff that we talked about before the first test too. And I've mentioned this before, but I think the most effective way to prepare for this exam or any of my exams is go back to problem set one, problem one, read the question, and ask yourself, can I think of the steps that it takes to solve this problem? And if you can go, I do this and this and this and this, then you probably don't need to waste time anymore on that one. Go on to the next one. And then, eventually you get to problems that you don't understand so well, and then spend some time on those. And in that way, you can just refresh your memory on everything we've done. Yeah, question?
You will give us all the equations.
Yes, that's right. Yep, all equations will be given. Anybody have any questions, other questions about the test? Okay. So we're working on stuff that's unrelated to the test. Before we go to that, does anyone have any homework questions related to the test that you'd like me to clarify or anything like that? Or any old topics that you'd like to talk about for a second? Yeah. Okay, so you got this cylindrical tank, easy cross-sectional area. It has a drain at the bottom. We're given the cross-sectional area of the drain, and we're given a function for the exit velocity of the water. And that function depends on the water height. It initially contains this mass of water. We're given the density. How long until it contains 900 kilograms of water? So cylindrical tank means the cross-sectional area is the same the whole way down. So we have something like this. We're starting with some given mass of water. The cross-sectional area of this drain is So this water is coming out at a speed of square root of 2gz, and at any instant this is z. Conservation of mass is, it comes into this, but a lot of the calculations are sort of working around that thing. So let's get into conservation of mass. So dm dt inside the control volume is equal to m dot at the inlet minus m dot at the exit. Is this steady state? No, right. The mass inside that cylinder is changing, so we have to keep everything here. There's no water coming in, so this goes away. There's only water exiting. And we're not given too much in terms of, like, we have this function in terms of the height. So let's relate the mass to the height to start with. Okay, so here's the relationship between the mass in the control volume and the height z. Well, the mass is equal to the area times the height times the density. And so that is 1 times z times 1,000. So that's an expression for the mass.
Why the area is one?
What?
Why the area is one?
That's given in the problem, 1 meter squared.
Oh.
And the reason I did that is because we're also going to have me dot expressed in terms of z. So let's figure that out. So me dot, remember this formula we use all the time in this conservation of mass stuff, is that this is equal to the area times the speed divided by the specific volume. Remember that specific volume and density are interchangeable. If you know one, you know the other. They're reciprocals of each other. So we could also write this as A times the speed times the density. That cross-sectional area of the exit is 3 times 10 to the minus 4. The speed is given as this function of z, and then the density is 1,000. So this is 1,000 times 3 times 10 to the minus 4 is 0.3. Multiplying that by square root of 2gz. I'm going to put this in as a number. So square root of 2 times 9.81 is 4.43, and then I'm multiplying that by the 0.3. So this comes out to be 1.33 times the square root of z. So I'll write it like that. And then this one Well, we're trying to plug this stuff into this equation for conservation of mass, the one above. Um, so I'm not quite where I need to be yet. I got m as a function of z, but what I really want is dm dt as a function of z. So dm dt is d dt of 1000z. And so that is just, I wrote this wrong. This is the time derivative of 1000z. So d dt of 1000z. So that comes out to be 1000 dz dt. Any questions about that? So now I'm going to plug this into my big equation. So 1000 dz dt is equal to 1.33 z to the 1/2. And now this is a matter of separation of variables. I'm not going to make you do any kinds of differential equations on exams, but this is a good thing to get used to seeing, try to struggle against it a little bit when you see it. Anytime you see an ordinary differential equation, so no partial derivatives, what you're hoping is that you can solve it by separation of variables, which means get all the t stuff on one side and all the z stuff on the other side. So I'm going to do this as well. First, I'll just get a single constant. So we have 751.88 dz dt is equal to z to the 1/2. And now I'm going to multiply both sides by dt. That dt is the only stuff we have that has t in it. But I do have to move the z to the 1/2 power over to the left side. So this is 751.88 z to the, in order to move that over, I have to multiply both sides by z to the negative 1/2. So this is z to the negative 1/2 dz is equal to dt. And now that I have only z stuff and a dz on the left side and only t stuff on the right side, I can integrate both sides. This, as always, is from state 1 to state 2. This is from state 1 to state 2. And we're trying to find the elapsed time. So we can think of, well, let's integrate and see what we get. So this is 751.88 z to the 1/2 divided by 1/2. So multiplying this by 2, you get 1503.76. And this is evaluated from whatever z is at state 1 to whatever z is at state 2. And this one we can just think of as t evaluated from state 1 to state 2. That's just going to be, you can think of that as just like the elapsed time. That's what we're trying to calculate. Or if I don't, let's just go through the full thing. So you get t evaluated from state 1 to state 2. And so this T at state 1 we'll call 0. T at state 2 is the T we're trying to find. So I'm just going to call it T, We're trying to find that T. Okay, what about this one? We're really close to getting this now. The only thing we don't know is we don't know what Z is at state 1 and state 2, but that's pretty easy to find. So the last step is Z at state 1 and Z at state 2. State 1, we know that the mass is 2,500 kilograms. And that's equal to the area times the height times the density. So that's 1,000 Z. And so Z is equal to 2.5 meters. And then at state 2, the mass it was 900, I think, 900 kilograms. That's equal to area times height times density. And so Z for this is 0.9 meters. Now plug that into, so we're going 1503.76 evaluated from 2.5 to 0.9. Whoops. I left out the Z to the 1/2. I'm missing a negative sign here. This whole thing I'm missing this negative sign, so sorry about that. Our dmdt is 1000 dz dt. This is our m dot exit, so this needs to be negative. Okay. And so we have negatives everywhere. I'll move it over here eventually, move it over here, here. So we got negative 1503.76 Z to the 1/2 evaluated from 2.5 to 0.9 is equal to T. And we get T is equal to 951.1 seconds. So as far as a thought process on that, I mean, I guess as I do this, I just sort of keep talking like I know where I'm going with it. But, I mean, I know I'm going to use this equation. It's obviously, I mean, if you can look at this problem and recognize that this has to do with changing mass inside a control volume, then you know you're going to use this equation. And then just little by little, you can start figuring out how your things that are given relate to this, like what were the things that I knew? Well, I sort of right away knew that I could relate the mass in the control volume to the height. Okay. And it gave me this in terms of the height. So, okay, that's good, you know. Um, I could have gone in the opposite direction and said, I'm going to, instead of doing everything in terms of Z, I'm going to change all my Z's to being related to mass. And I could have done it all in terms of mass. That would have come out the same. But I knew there was a relationship between those two things that I could find. And I always, when I'm thinking of conservation of mass, I'm looking for places that I can use this relationship where m dot is equal to the area of the aperture times the speed divided by the specific volume. So uh, so I had that relationship, and then I'm just putting all this stuff, combining this stuff until I have an expression that only has t and z or t and m in it, you know, that just has t and some other variable. And then it's differential equations, which is not really something I cover in this class, but you know, little by little, you want to sort of get used to seeing simple differential equations and, you know, having some ideas of how you might solve them. Like over little by little over your 4 years of undergrad, you know.
Professor,
Yes,
when did we do this problem the first time?
quite a long time ago, but I
The sixth, I think. It was like
oh, of October.
yeah.
Okay,
October
that's
6th.
not so long ago.
Okay. That's like the day I had it. I was.
Okay, yeah, could be. Any questions about that problem?
So we could solve it in terms of, because I think I remember we solved it like the other way. Instead of using Z, we used the amount
The mass.
of liquid
Yeah,
through the mass. Like we could do
right.
it either way, basically.
Yeah, sure. Because you have so what you know is that you have this relationship. uh, what's the? We know that m dot uh, is equal to. Mm,
We
well,
solved
you
it
yeah.
all
So
the
you
time.
can. So you know that m is equal. I think this. I think that would be a little more tedious. You could do it, of course, but
Just trying to find where we did it because I remember
mm,
we did this problem before.
okay. You could do it, but it would be more tedious. I think this is definitely a more straightforward way to express it all in terms of z.
Okay.
Any other homework problems you'd like me to go over related to the test?
Yeah, we did do it in terms of Z,
Okay,
and we got
come on, 951.
951.9 seconds.
Oh, okay, we'll call that round off air.
Yeah.
Um, yeah, any other homework questions? Otherwise, we're getting back into weird stuff, voodoo thermodynamics for in honor of Halloween. We're talking about entropy. What?
This is going to be on Halloween, the second exam.
Yeah, but there's no voodoo stuff on the exam. Entropy brings that stuff up for the first time in the second law of thermodynamics. Okay, so we're back to the second law. And remember, we have three forms of this. The first one is the Clausius statement. And that's the intuitive one that says that if you're not doing anything tricky, heat is always going to transfer from high temperature to low temperature. The second one is the Kelvin-Planck statement. and that says if you uh, generate work using a heat engine, uh, some energy is always lost in exhaust. That rhymes. And then the third one that we're working up to uh, is the entropy statement. And that says in any process, the entropy of the system plus the entropy of the surroundings is greater than or equal to 0. And that entropy is a type of thermal disorder. So if your room is messy, you look for your favorite Taylor Swift record and it's hard to find. If your energy is messy, it's not that you don't have a Taylor Swift album, it's just hard to get it. If your if your thermal energy is messy, it's not that you don't have that energy, it's just that it's very hard to use it to produce work. So that's what this is when people talk about thermal disorder. Um, and so we talked about the Kelvin Planck statement last time. Now we're going to work our way towards what entropy is. So we're on the way to defining entropy. I know you kids love your Taylor Swift.
Sure.
um, Kids today. Okay, the first step in defining entropy is this thing, and this is where you have to be careful. It's called the Clausius inequality, and it's totally unrelated to the Clausius statement. Well, they're mathematically equivalent, but you have to think about them totally different ways. Um, so it's mathematically equivalent to the Clausius statement, but it's very different. Let's say very different intuitively, like the way you have to understand it. And it says that for any cycle, and from now on, talking about entropy, we have to always be really careful in our heads about, are we talking about a perfect ideal cycle with no irreversibilities, no friction or anything like that? Or are we talking about an actual cycle that you could see out in the world? And so this is for any actual cycle. Um, so actual means it doesn't have to be reversible or internally reversible. And the cycle means that from the beginning to the end of the process, all properties are unchanged inside your system. All properties of the system are unchanged. And for any actual cycle, um, so if you take the entire sum over this cycle, that's what this means. We're talking about a cycle um, of heat exchanged divided by the temperature where that heat is exchanged across the boundary. And if we do this for the entire boundary, this has to be less than or equal to 0. Um, so this symbol means we're talking about a cycle. This means over the whole boundary. And so there you go. That's the definition of the Clausius inequality. Oh, there's one more thing, actually. Sorry. Uh, and if the process is reversible, then that's when you get the equality. This integral is equal to 0. Okay, so that integral always has to be less than or equal to 0, and it can only be 0 if it's a reversible process. Okay, this is ugly looking, but you can think of it in sort of a simpler way. So think of it as, instead of that integral thing, think of it as just the sum of all the places where heat is transferred across the boundary divided by the temperature where it's transferred around the entire boundary. So, like, for example, if the only place that heat is exchanged is at one part of the entire boundary, and you know the temperature where that heat is being exchanged, um, then it's just the amount of heat divided by that temperature that you know. Okay. Um, so I can give you kind of an intuitive idea of how the Clausius inequality works. Um, so let's just think of um, a cycle where the only things happening are heat enters system from a high temperature reservoir. So I'll call that TH. Um, and we'll say uh, let's call that TH 300 Kelvin. And the amount of heat, let's give that a number 2. Let's say that that's 1,000 joules of heat. And then heat leaves the system at a cold reservoir of 200 degrees Kelvin. And if it's a cycle, then the amount of internal energy inside the system can't change. So this also has to be 1000. So now let's calculate that ugly integral thing. So
What is 0 again?
what is 0?
So
Oh,
you said that the
if it's a reversible process, then when you do
yeah.
calculate all the heat exchanges divided by the temperature, it'll be equal to 0.
So how did you call it again?
What?
So the something is 0, and that means that the heat in is equal to the heat out.
Oh no, the heat in is equal to the heat out because it's a cycle.
So because it's a cycle, it's always 0?
No, we haven't calculated that integral thing yet. All we've done, I just said that. So I said, okay, let's say that the heat coming in from the boiler is 1,000 joules. Then we know it also has to be 1,000 joules leaving if it's a cycle.
Okay.
And I just made up two temperatures. But obviously, like if you have a high temperature region and a low temperature region, they have to be different. Okay. So now we're going to calculate this integral. So the integral of squiggly dq, that's just like a tiny infinitesimal increment of heat exchange divided by the temperature where it's exchanged all around the boundary. You never have to think about it this way in this class. You can just think of it as the sum of, it's always just going to be finite heat exchange at a temperature. But this is one of those things where if you write it like this, people think you're smart, So it's good to keep that in the back of your mind. But this is what it really is to us. Okay, so now let's calculate this. What's the sum of the heats divided by the temperatures? And we're going to use the first law sign convention. So the heat coming in, what's Q? Positive 1000, yep. And what's the temperature where that heat is coming in? Yep, 300. And then heat is leaving the system, so that's going to be negative 1000. And what's the temperature that 200? And so now you see, we have a bigger denominator on the positive, a smaller denominator on the negative, and this comes out to say 1.6 repeating joules per Kelvin. Okay. So for this cycle, you can see that in order for it to obey the rule that heat only spontaneously moves from high to low temperature, you have this effect of this integral coming out to be negative. And this is not something we're going to use a ton, although the idea of it is important. Okay. So why is this important? So why is the Clausius inequality important? Entropy comes from this idea. And so the definition of entropy, you're going to see the connection to the Clausius inequality. And the definition of entropy is maybe the first time you see it, it's surprisingly like abstract. Okay, it's not something uh, you can't design a thing that goes and measures entropy. Okay, it's a very mathematically defined thing. But the definition of entropy is this: the change in entropy from state one to state two is the integral from state one. I'm going to write out state one since this is also an S of this increment of Q divided by the temperature where it's transferred all the way along the boundary for an internally reversible system. Um, so, two things to notice about this. I guess let's box this. This is important. And the two things to notice are, first of all, this definition doesn't work for actual systems. It only works for these theoretical perfect systems. Whereas that Clausius inequality was for actual systems. Okay. And then second, um, notice that the Clausius inequality was for cycles. This is not necessarily a cycle. This is for any two states. Um, and let me say a little more about this number two. In fact, entropy is a property so the change in delta S is equal to 0 for a cycle.
What does it mean when in the calculator it says that the entropy is like something something joules per kilogram?
Yeah, so, well, first of all, that's a good, let's get that in your notes here too. The SI units for entropy are joules per kilogram. So that's part of it. Um, so what does it, so what does it mean? So it means that if, I mean, I guess, so, oh, as opposed to like just a difference in entropy, like when it gives a,
Yeah.
okay.
So we use it as a difference?
So yeah, it's always in our equations going to be used as a difference. So in a way, it's arbitrary what you call zero entropy. Um, you know what I mean? Um, because it's always going to appear as like how much is entropy changed. Um, but you know what it means if you have two different states and your calculator gives you an amount of entropy at both of those two states, it says that if you used an internally reversible system to get from one state to the other, that is how much heat would have to be exchanged over at the temperature boundary.
So is that linked to enthalpy and internal energy?
No, it's really not related to enthalpy. I mean, everything's connected in some way, but um,
Like we've been comparing enthalpy, right? So
in this class,
yeah.
yeah. So far, it's only been enthalpy. Now we have this new property called entropy that also appears in tables and websites and stuff.
Okay.
And the way they calculate entropy for tables is very complicated differential equations using this definition. But it's going to turn out to be a really useful idea, even though it's a very abstract idea. Okay. Any other questions right now?
So the CI unit for them is joule per Kelvin?
Joule per Kelvin. Yeah. And you can see that from you can just see it from this definition here that the Q here, where's my cursor? The Q is in joules, the T is in Kelvin. Okay. And we're going to usually be using specific entropy, which is joules per Kelvin kilograms. Okay, that's all for today. So I won't give you a homework assignment tonight, and then
We got the test
test on Friday. Yeah,
in 2 days.
2 days.